Okay, yeah, there you go. All right, hi everyone. Yeah, my name is Maris. I'm from the University of Siegen, from Professor Christoph von Laven's group and Professor Möller's group. Today I want to talk with you about recent work of mine with my two doctoral supervisors called Temporal Action Localization for Inertial-based HAR, so Human Activity Recognition. First, a bit about myself. I started in academia with a bachelor's in information systems from the University of Cologne, actually at one of the professors who's now at KIT. I finished then and moved over to my master's in data science here around the corner in Mannheim. And I'm now doing my PhD in computer science at the University of Siegen. To much of the surprise also here in the audience, yes, I have two doctoral supervisors. So I'm part of two groups, twice the team meetings, twice the benefits from being part of two groups. So my first doctoral supervisor is Christoph von Laven, who some of you might know. He's been in the UBCom community for quite some time. And the other professor is Michael Möller, who's the head of the computer vision group. So hence also my doctoral project being twofold, many times. Yeah, so the stuff or how I'm going to start the talk today is actually with a quote that I've come across many times already during my 3 years in research when it comes to work in the wearable activity recognition community, especially in the deep learning community. Many times I was faced with people asking me, well, but does this work for wearable activity recognition? And what I mean by this is that there's been this persisting trend in deep learning, not only in our community, but also in many other communities, that people find out interesting stuff, interesting concepts. And these concepts are not only applicable to their community, but also very useful for other communities. So in the wearable activity recognition community, we've seen now that, for example, attention mechanisms, data augmentation strategies like mix-up, or also complete architectures are applicable to our community as well, and have shown to really improve the results. Talking about the inertial-based human activity recognition community, well, what they're faced with is this window-based approach of trying to evaluate their classification algorithms, which aim to really classify step-by-step a timeline of which activity is happening at which moment. And they're usually dealing with these like classic classification metrics. So their point of view to the whole problem is we chunk the timeline into different steps, we classify each step, and then each step gets compared to a ground truth. But of course, one can ask the question, what do other communities do? What, for example, does the vision community do? Because we're dealing with inertial sensors, we're dealing with, for example, accelerometers, but of course, you can also translate this activity recognition problem to, for example, videos. And during my research, I came across the Temporal Action Localization community, or TAL community, which is the closest what we have to the inertial-based community. And this community aims to localize, if I give them a video, aims to localize all activity occurrences in that video, in this untrimmed video, from start to end. So say I give you a recording of my workout routine, you tell me at which point in the video I did which activity and for how long. And of course, their approach is this segment-based approach. So they're dealing with segments which they're predicting. So they're always predicting triplets of the activity start and end time, and then evaluating the algorithms also more from this segment-based perspective. So not this classification perspective where we're classifying each timestamp, we're classifying complete segments in the stream. And they're also borrowing then more metrics from other areas, such as object detection, where we're treating the timeline as a picture, where we're drawing bounding boxes on, which represent the activity during the activity occurrences, and then we're comparing the overlap of these drawn activity occurrences to the ground truth. What this actually means, I'm going to show you in a bit. But yes, so what I'm going to show you today is that these vision-based models can actually, I'm going to show you today is that these vision-based models can actually be applied to inertial-based data and actually in a plain fashion, which is quite surprising. Yes, but first, let's talk about these two communities. So the disjunct communities, both not really related to each other, except their ultimate goal. First of all, the inertial activity recognition. So what they do, I already told you, like they're usually starting out with chunking the timeline into sliding windows, meaning that you take the prediction stream and you group together all this, for example, 50 records, which then represent 1 second in the activity stream. You do so in a rolling fashion until you have covered the whole stream, where it's like chunks of 50 samples always belonging together. And then you try to take those grouped together representations of your timeline. You feed those individually through the deep learning model, which then tries to find patterns which are reoccurring, but also like maps these patterns across time within the window. So if we have reoccurring patterns within the window, these can be learned. And then we make predictions for these. Then we make predictions for all of these chunks that we have. So we classify them, for example, here in this example, into 3 categories. And then we compare these categories or these predictions to the ground truth stream that we have, which is also then applied, of course, same chunking. And then what you have is, what you then calculate in the end is classic classification metrics. You're always comparing 2 pairs, a pair of predictions and ground truth, and see, do they match, do they not match, and then you can calculate these classic classification metrics. The temporal action localization community, on the other hand, also starts with chunking the video into clips. So for example, they also apply a 1 second sliding window where 1 second video clips are created out of the video stream, which with some sort of overlap, for example. But what they do is they do not work on the raw data. So you usually do not work on raw images. What they apply is then some sort of feature extraction on top of these clips to extract feature embeddings of a certain size using some pre-trained feature extraction methods. And these embeddings then represent, for example, information of the RGB information or optical flow information. They're then one-dimensional embeddings, which are then, similarly to the inertial-based community, fed through deep learning models again. And these deep learning models then, like I said, also don't predict just every time step itself, but try to classify segments rather than classifying the windows. And what you then end up is these triplets. So saying, I have seen activity 1 happening from the 1st second until the 4th second, and so on. And then you map what you predicted, so the prediction timeline as a whole. You then compare the predicted segments with what you have in the ground truth. You see if there's some certain overlap, and if this overlap then exceeds a certain threshold, you say like, yes, I correctly identified that activity. So these thresholds you can then define, of course, different strengths. So saying like I'm testing a very low threshold, saying it's okay, then I only spotted an activity for 30% or something. You can increase this threshold to be more restrictive, to be more strict. But in the end, yeah, this is the 2 communities. This is their approach to solving the problem of finding activities. Now, if we want to evaluate, of course, the temporal action localization community on the inertial-based datasets that we have in the community, we of course first need to identify what is kind of the state of the art in the temporal action localization community. And if you go to these nicely documented vision websites where everyone's posting their benchmarks, for example, papers with code, they have their large benchmark datasets there, and algorithms then get evaluated there, and everyone posts their benchmarks there. You can see that 3 models kind of stick out, and these are the ActionFormer, Temporal, Maxa, and Trilad model. These have all been released within the last 2 years, the ActionFormer being the first instantiation. And these are single-stage temporal action localization models, so they can go through this whole prediction pipeline within 1 single step. So coming up with segments and also classifying these segments in one single training step, so end-to-end learning. They have broken significantly the benchmarks the last 3 years, so there's quite the gap. And they have remained the state of the art now for 2 years, which is in the vision community quite long. Yes, so let's look at one of these models. I'm not going to go into much detail about the architectures. I'm just going to highlight maybe also like stuff which kind of is same as what the inertial-based community does, but also what they do differently in their community. And here's the architecture overview of the action former. So this was the first instantiation of these types of models. They follow the encoder-decoder structure. So meaning that we're first encoding our feature embeddings into a latent space, and then trying to decode that latent space again, making predictions, in our case, the segments, as well as the class labels of these segments. Similar to what the inertial-based community does, they first also apply convolutions. But then what's interesting here is what the authors also claim makes up the strength of the models is that they're downsampling through transformer layers the feature embeddings of each video clip to be, in the end, only, for example, 1/32 of the size. And this basically makes it such that these feature embeddings also represent information at different temporal granularities. So in the beginning, you're being quite granular in your prediction timeline, which you're classifying, and then you're being with a quite wider receptive field of what you're trying to classify. And the interesting thing here is that they then take these embeddings, and all of these embeddings get classified, meaning that we're classifying basically video clips multiple times at different temporal granularities. And these video or these classifications by the decoder are then also shared across these layers. So this kind of feature pyramid that they're creating, they're then classifying all of these timestamps. So the same clip gets classified multiple times, such that they're claiming they're leveraging or are able to also detect short activities, but also long activities, and kind of like fit it towards the nature of how the activity appears in the prediction stream. This is only possible with this downsampling, the authors claim. Yes, so if you want to read more about these models, I highly recommend you read the papers. Of course, this is just a rough overview. For the other two models, they're basically advancements of the original action former. The Temporal Maxer, for example, also only just removes the transformer layers and just uses downsampling, because they claim that the embeddings which are created, for example, by the feature extraction method are already discriminative enough, and they show in their analysis that the results speak for themselves, and they can achieve, with a much simpler model, better results in some data sets. The TriDat model kind of goes towards replacing the transformer layers with SGP layers, which are fully convolutional, more lightweight, and do not suffer from rank loss. So their model is also more fast than the action former. And they also extend the regression head to be a trident head, hence the name TriDat. And the trident regression head then basically better optimizes for action boundaries. So it's an advancement in itself, and I'm not going to go into detail. You can read it in the paper if you want to. In the end, all these models share the same style of architecture, but yet apply different complexity levels and also different ideas how to better refine, for example, the boundaries of each activity. Now, in order to train these models, of course, we first have to think about how do we translate what we have in inertial-based hard such that it's applicable to these vision-based models. And like I said, these temporal action localization models work with one-dimensional feature embeddings, which we don't have in the inertial-based hard community. So what we get from the 2D from the windowing approach, from the sliding windowing approach, is these 2D window of data. So for example, here you can see it's 4 sensors with 3 sensor axes each. And then we're grouping together 50 records always of these 12 axes. So in the end, we're left with a feature dimension vector of 50 times 12, so 2-dimensional data. What does the trick here? Actually, how we can feed even raw data to these temporal action localization models is we just vectorize it. So we're concatenating all the axes. So in that case, for example, for the first sensor, we're taking first the x-axis, then afterwards comes all the records of the y-axis, then the z-axis, then comes the upper sense, and we do so until we have one concurrent vector, which is basically just each sensor axis appended after each other. This feature vector is then, of course, of size 12 times 50, so of size 600 if we assume 50 samples. And then we have a one-dimensional feature embedding, which represents what this 1 second video clip represents as far as IMU data. And this really simple trick has already shown to work on one data set, which I'm going to talk about later. But of course, this approach, we really want to dive deep and see how does it work or how does it perform on a multitude of human activity recognition data sets. And for our benchmark data sets, we use then 6 data sets. So we use the opportunity data set, the SPHER data set, the wet lab data set, the WHERE data set, and hang time data sets, both data sets from our group, and the real-world HER data sets. These data sets differ, of course, in size and number of classes, the application scenario, also number of sensor axes, many of which have only periodic activities like locomotion activities. Some of them have also complex activities or non-periodic activities. In the end, they're all different from each other. One thing to point out here is, of course, that the real-world dataset is the only one which doesn't have a NULL-class, which will come in, which will be interesting during the benchmark analysis, you will see. Yeah, we take those 6 data sets and then we evaluate these 6 data sets. We take 4 popular inertial-based architectures. So we take the DeepConf LSTM from Madonius, the shallow DeepConf LSTM from our lab, the tandem discriminant from Abedin, and the TinyHAR from your lab. And we take those 4 models and compare them now to the 3 temporal action localization models, which I talked about. So Action Former, Temporal Maxor, and TriDet. Now, for the training procedure, we apply leaf on subject out cross-validation, repeating it 3 times, meaning so 3 times a complete iteration of the leaf on subject out cross-validation, each time applying a different random seed, such that we're seeing that improvements are not just a result of statistical variance. For the inertial-based HAR architectures, we're applying 100 epochs training, a stepwise learning rate schedule, glorid installation, so the standard stuff which we also applied or which is mostly seen in the inertial-based papers. One thing to point out here, of course, the batch size for these models we fixed to 100 sliding windows. So in each iteration of the network, 100 sliding windows get classified. For the temporal action localization models, we use them in a plain fashion. So we up the number of epochs. So in the original publications, they used way fewer epochs, but also because the data sets are larger than the inertial data sets. So we use also 100 epochs. And of course, we have then 2 losses because we're dealing with the classification loss and the regression loss. Here, the authors use the focal loss, and for the regression loss, they use the IOU loss, both of which originate from the object detection community. And what's also interesting here is that one batch in this community or in this architectures always represents one complete untrimmed sequence of one subject. So we're predicting for one subject a complete prediction stream in one go, in one batch. And how they do this to also limit their, of course, the complexities, that they randomly truncate the amount of windows that we have, because we, of course, have arbitrary sizes of each subject's prediction stream. They truncate it to always be 2,304 windows. Then for post-processing, so we do some post-processing for the inertial-based data, for the inertial-based architectures. We do apply majority filters to go over the predictions, because what you can see is if you just apply the inertial-based architectures in a plain fashion, what many times happens is that there's just these one-off wrong predictions. So many times the prediction stream is quite scattered, where there's a lot of activity switches happening in between. And this majority filtering kind of is aimed towards eliminating those activity switches to give them a fairer comparison, because they're not optimized to predict long coherent segments. So if you don't do this majority filtering, what happens is metrics like MAP, for example, are close to zero, because there's just no long-lasting coherent segments in the activity stream. And we've seen if we apply just a majority filter of 15 seconds, the prediction stream gets more smoothed out, and you can see more of these longer lasting segments actually, and MAP scores also rise. For the temporal action localization community, the post-processing that replies that we do some score thresholding. So the thing is, if you don't do any score thresholding, the algorithms are set to classify every timestamp into one activity, meaning that a NULL-class gets completely disregarded, and basically every timestamp gets classified as one activity. And if you just apply some score threshold of, for example, 0.2 confidence that is associated with the segment, the lower scoring segments get eliminated and breaks appear in the prediction stream. For this, you can also see within the paper, we made a visualization of this. Now, quick interlude to shameless plug for our research group. So one of the datasets that we feature in there is the WHALE dataset, which is a dataset which I recently worked on, which I put a lot of effort in. So I recorded 18 participants doing sports activities outside. So these people were tasked to do a minimum of 2 sessions. So it was 18 activities, 18 workout activities, ranging from running, stretching to also strength-based exercises. And yeah, these were all done outside, changing weather conditions, changing seasons. So I think it was recorded over 5 months. So we also have some snow, of course, in there because it's in Siegen. In total, I recorded 15 hours of data. So we provide vision data as well as IMU data, 615 action segments at 10 outdoor locations. The cool thing about the WHALE dataset is that it's really easy to replicate and kind of like a real-world sensor setup. So we try to make it as realistic as possible how people would do sports outside, what IMUs would they equip to their body, as well as what would be a realistic camera setup. The sensors are equipped to the hands or to the wrists and to the ankles. So we have 4 sensors in total, and the GoPro is head mounted and kind of tilted such that like in a wide field of view, everything is captured. Yes, and easy to replicate because, well, you can just equip the sensors, go outside, record yourself doing sports, and then the whole thing is, yeah, easily extendable. Now, talking about the benchmark results. So how do these temporal action localization models actually stack up? Now, what we've seen is that across all the 6 datasets, as expected, the temporal action localization models are actually able to predict more coherent segments, which show a larger overlap with the ground truth. So as you can see with the MAP scores, the improvements range around 20 to 30%. For the real-world dataset, even almost 70% MAP, where the inertial-based architectures were not able to show any overlap large enough with the ground truth, such that it could be recognized as a correct prediction by the MAP. As far as prediction performance, we see that for 4 out of 6 datasets, the F1 score is actually higher. So the best temporal action localization architecture outperforms the best inertial-based architecture in 4 out of 6 cases, with the improvements, for example, for the SVHR dataset being quite significant, with around 15% F1 score improvement. Now, you probably ask yourself, where do these improvements come from? So as you can see here, this is the coloring is not so good, but this is the confusion matrices for the SVHR dataset for the best inertial-based architecture. So this was the shallow deep conv LSTM, and the best TULL architecture, which is the trident model. And you can see that especially the NULL-class accuracy is quite high for the temporal action localization models. So breaks get usually better identified. But also what the inertial architectures usually struggle with are these transitional activities. So the SBHR dataset consists of locomotion classes, but also includes these transition classes. So the period from going from sitting to standing, from lying down to standing up. And these are really short, non-periodic activities, and especially these activities which might get especially well predicted from the context, because if you know that you've been sitting, then the likelihood that sit to stand is happening or sit to lie or whatever is higher than if you would be sure that you predicted lying. Here, because the temporal action localization models take more context outside what they're predicting, outside what the window that they're predicting, they know kind of like the complete timeline. These activities get exceptionally well predicted. But also we see that the temporal action localizations architectures actually struggle. So here, for example, for this really simple data set, the wearable data set, somehow the classes get confused, which previously we were not confused with. So for example, here it's climbing up and climbing downstairs. In other data sets, for example, the SBHR data sets, these activities were quite well recognized. And now all of a sudden, these activities get confused. And also activities get confused which don't make any sense. So for example, here there's a large confusion between jumping and lying down, which from a logical standpoint does not really make sense. Of course, you have to say that the wearable dataset is the only one which does not have any breaks, and it's kind of this artificial dataset, which is like activity segments cut together. So it's all the breaks were cut out manually by some researcher and then concatenated after each other. And one assumption of us is that it might be that in this case, for example, the breaks are important for the temporal action localization models to properly learn. Also, this data sets consist only of really large chunks of segments. So in the end, our training data sets is usually per subject only 5 segments. So 5 training instances, which is quite small, of course, to train an algorithm with. Yes, so now takeaway messages. We showed that TULL architectures are actually applicable to inertial-based R and in the plain fashion. So we did not do any hyperparameter tuning per se, we just increased the number of epochs. The strengths of the TULL architectures, well, they show overall a less fragmented timeline, which they're predicting. They're showing the highest MAP score across all 6 data sets. And also they mostly predict all types of classes reliably. So especially evident by the confusion matrices, one can see that usually the TULL architectures don't struggle with any type of activity and are kind of giving reliable predictions across the board, whereas the inertial architectures sometimes struggle, especially with these really short-lasting or small activities, these transition activities. And in general, they do not score the highest for most activities, but they are giving a reliable prediction for any type of activity, and thus also score the highest average F1 score for 4 out of 6 data sets. Also, breaks get quite well recognized, so the NULL-class accuracy is the highest across all data sets. Now, of course, these TULL models offer many unexplored concepts for the inertial-based R. They're a different perspective to activity recognition, so they're more of like this retrospective analysis of a timeline where you feed the complete thing in, and you want to have the complete analysis of a prediction stream as a whole. They do treat this whole problem differently. They have their different metrics. So mean average precision is something which I've not seen in activity recognition papers in the inertial community, because they treat it more of a segment-based approach. And well, they predict segments rather than window labels. And what's also interesting is they're trying to learn temporal context across windows. So how we in the inertial community apply temporal aspects and architectures is usually really focused within videos. So you try to learn only temporal dependencies within a window, but you're disregarding how do these windows amongst each other relate, or what is happening maybe 15 seconds ago. Could this 15 seconds ago kind of like help us in the prediction? There, the temporal action community tries to also scale down the complete timeline at different granularities and then benefit from looking at the timeline at different granularities. So they're really giving, in my opinion, a new perspective, new concepts, which are of value, of course, to our community and which should be further investigated. Yes, that concludes my talk. So there's the paper. It's a preprint if you want to read about it. Also, of course, if you want to connect with me on LinkedIn. Yeah, that's it. I'm going to stop the recording now, and then we can move over to a Q&A session. Thank you for your attention.
Yeah, thanks. Just started.